Welcome to the Big Picture Podcast. For today's episode, we'll be looking at the amazing covalent bond. Not the ionic bond, not the metallic bond, but the covalent bond itself worthy, of an entire episode. Now, with us today is no one but me and you, the listener. Tracy's on the road, JW has returned back home. So I was thinking perhaps you, the listener, might want to jump in as our virtual co-host. Huh? Yay! Great. Okay. Then might you please introduce yourself? Welcome. And together we are going to parse out the main details of that covalent bond. Let's begin. Okay, so what resources do we have here? Well, we've got the book. We're going to be going through pages of the book, and I have my pen and paper for notes. Perhaps you have that too, or perhaps you're just driving along and ready to get a basic overview of this stuff. We've got myself, and we also have you. All these resources together, you know it's going to happen. So the covalent bond. To dig into the covalent bond, we're going to need to back up a little bit to review the ionic bond. Recall what happens there is you have an element that tends to lose an electron, and that's usually a metal atom. And it will lose that electron to another atom, which tends to be a non-metallic atom. And as that metal atom loses an electron, it forms as a positively charged ion. And as the nonmetal atom gains an electron, it becomes a negatively charged ion. And what do you know about two oppositely charged ions? How do they feel about each other? That's right. They like each other very much, and they're going to come together because opposite signs attract. And those two oppositely charged ions are held together by that electrical force, and we call that electrical force the ionic bond. It's the force of attraction, the electric force of attraction between two oppositely charged ions. Yeah. So what about a covalent bond? What happens there? Imagine you got two kids sharing toys. What is it that holds those two kids together? Yeah, they might be friends and all, but, think of it this way. The kids love the toys. And so if you have two kids, each kid with one toy, and they get together, you have a situation where each kid now has access to both toys. Now, wouldn't you rather have two toys than just one toy? And that can happen when the two kids are sharing their toys. So, same thing with atoms. You'll have one atom that likes its electron. It's not going to lose its electron. And then you have another atom that also likes its electron. It's not going to lose that electron. And, of course, these tend to be nonmetal atoms, those to the upper right side of the periodic table. If you could bring those two nonmetal atoms together, those atoms could then share their electrons so that each atom has not access to one electron, but two electrons, its own electron plus the electron of its neighbor. Let's look at this from the point of view of a hydrogen atom. Okay, what is a hydrogen atom? This is where you go ahead and describe the hydrogen atom. Yeah. You've got a proton in the nucleus and an electron whizzing about it, right? And we talked about the shell model where the electron is, say, if the hydrogen atom, it's in the first shell, and it's whizzing around that nucleus, much like a bunch of bees might whiz around a very sweet flower. Yeah. And when we talked about the shell model, recall that there is a capacity for electrons for each of the different shells. And the first shell has a capacity for 2 electrons. So The hydrogen atom. Think. You've got a proton and a single electron whizzing around that proton within the first shell. You with me? But that first shell has a capacity for 2 electrons. Might it be possible to have 2 electrons whizzing around that nucleus? Now, the nucleus, it's just one proton. We're talking about the hydrogen atom, and it's just one proton. Is it possible to have 2 electrons whizzing around that one proton? 2 electrons around one proton? Yeah, actually it is. How so? Because that first shell has a capacity for 2 electrons. Well, what are you going to have there? You're going to have a hydrogen atom with one proton and 2 electrons. Wait a second. We talked about that. When you have an atom that has a different number of protons versus electrons, what do you call that? Very good. Everyone together. An ion. You have an ion. This ion is that going to be positively charged ion or a negatively charged ion? It's negatively charged because it has 2 electrons and 1 proton. The electrons are negatively charged. You get 2 of them. You get 1 proton, which is positively charged. The net charge there is going to be -1. We've just described the negatively charged hydrogen ion, sometimes called the hydride ion. The main thing for you to understand is that there can be 2 electrons around that 1 proton, just as there can be 2 bees hovering around a sweet flower. I know you might think that, well, here's 1 electron and here's 1 proton, and the 2 are going to neutralize each other out so the net charge is 0. No. Don't think like that. Think about the flower. The flower has this sweet aroma that's spreading out into space. And if there's room around that flower for a bee is going to go there. Why? Because the bee is attracted to that scent, to the sweet flower. Likewise, if you have a positively charged proton just hanging out in space, you bring in 1 electron. Yeah, the 2 add up to being neutral. But the electron, say, is on one side of the proton. There's still the other side of the proton that can still attract another electron. So the positive charges don't disappear. They are there. And when the second electron comes in close enough, it will be there, much like a second bee around that sweet flower. I'm belaboring the point because it's real important that you understand you can have 2 electrons around that 1 proton. And in fact, it likes to have 2 electrons around that 1 proton. So let's think about now of 2 independent hydrogen atoms. Each hydrogen atom, not ion, each hydrogen atom has a proton and an electron, right? And they're just hovering around in space. Then one day, the 2 atoms meandered close to each other. And the electron of one hydrogen atom looked over and saw the proton of the other hydrogen atom and said, Meanwhile, the electron of the other hydrogen atom looked to the one hydrogen atom and saw that proton in the center, and it said, you with me? There is an attraction, an electric attraction between negative and positive charges. And so these 2 hydrogen atoms, they came together with the 2 electrons situated in between those 2 protons. And what has happened here is the shell of the first atom is now overlapping with the shell of the second atom. And in that region of where the shells overlap resides those 2 electrons. And what do you suppose those 2 electrons are spinning in opposite directions. Absolutely, they're spinning in opposite directions, right? If the electrons are to be close to each other in the same vicinity, within the same seat on the school bus analogy we had from the last episode, yeah, they're going to be spinning in opposite directions. But there they are, two electrons situated between two protons. Very much like two kids sharing two toys. Each kid puts the toy in between the other, and suddenly each kid has access to, not one, but two toys. That is a favorable situation. Just as when you have two protons with two electrons in between them, that too is a favorable situation. Now, let's check out what's happening here. Those two protons, in between them is sandwiched those two electrons. Now, are those two protons just going to go away? No, they're attracted to those two electrons. This is to say, those nuclei are held together by the electrons that are in between. They're stuck. They're held by an electric force. What we call that electric force here, where electrons are being shared, we call that a covalent bond. Co meaning sharing, valent meaning valent electrons. These are valence electrons that are being shared. Remember, the valent electrons are those that are found in the outermost shell. So in a covalent bond, you've got the sharing of valence electrons. Bam. Any questions? Okay, can you explain that, what we just did? Go ahead and hit the pause and use the bee analogy. Use the two kids playing with toys analogy. And then go ahead and describe the covalent bond. I know you feel comfortable, you don't want to do it, you just want me to move on. But you can do yourself a favor of actually doing it. You are, after all, the co-host. Go. Very good. Excellent, excellent. All right. Sorry for interrupting. Let's move on. Let's pick another atom. Pick an atom, any atom. Go ahead. Okay, fluorine. Let's do fluorine. Let's have two fluorine atoms come together. But first, describe for us the electron configuration for the fluorine atom. Go. Oh, the fluorine has 9 protons. It's number 9 in the periodic table, which means it has 9 electrons. Okay, go. Electron configuration for fluorine. You said, very good, that there are 2 electrons in the first shell. Right? Yeah, and 9 subtract 2 is 7. So that means there are 7 electrons whizzing around in the second shell. And the capacity for the second shell is 8. That's right. So you have only 7 electrons. That means there's room for 1 more electron. If you were to do an electron dot structure for fluorine, what would it look like? Okay, yeah. You'd have the F symbol for atomic symbol for fluorine. Write that out in a capital letter. And then surrounding it, you would use dots to represent the electrons. You'd go dot, 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 dot. Right? You'd have 3 pairs of electrons in one singlet. Right? 2 plus 2 plus 2 is 6, plus 1 is 7. Right? So think of that. The fluorine has a singlet electron. Let's call it an unpaired electron. And if one fluorine has one unpaired electron, another fluorine atom will also have one unpaired electron. So let's look at everything from the point of view of that unpaired electron within a fluorine atom. There you are minding your own business. One day, along comes another fluorine atom. And there you are in the second shell When you look down to the nucleus, you don't see the +9. You actually see something more akin to a +7 because there are those inner shell electrons in your way. But you're enjoying a +7, which is holding you pretty darn well. That's all within your own atom. You, that unpaired electron in the second shell of the fluorine atom. Now, you look upward and you see another fluorine atom coming your way. And you look up at that fluorine atom and you see something rather remarkable. You see the same thing because it's another fluorine atom, and that's remarkable. But you see 3 pairs in one singlet. It's not really the singlet that you see, it's the empty space that you see. And you're looking there and you go, in that empty space, if I were there, gosh, if I were only there, I would be enjoying a +7 nuclear charge. I'm negatively charged. I'm seeking out positive charges, and there's a +7. Wow. And you're going, but wait a second. I already have a +7 right next to me in my own atom. But getting a little greedy here, you look up to the other fluorine atom, and you'll see you could actually have your cake and eat it too. You could have 2 +7s, your own and somebody else's. And so the 2 fluorine atoms come together. And you, that electron, squeeze into that empty space of the neighboring fluorine atom. Oh, you see you have a partner. It's that other singlet who has its own intentions because it was looking at the empty space beside you. And everybody gets together. That electron fills up the space next to you, and you fill up the space next to that electron. And those valence electrons are being shared between the 2 fluorine atoms. And both those valence electrons are now enjoying a +7 from both sides. That's a capital yum from the point of view of those electrons. And that yum is an electrical force that now binds those 2 fluorine atoms together. They are bonded. What we have here is called a covalent bond. Okay, now notice what's happening here with a covalent bond. We happen to be working with atoms that are those that tend to gain electrons, and these are the nonmetal atoms. The situation we've just described here can occur when you have a nonmetal and a nonmetal coming together. They've got to be nonmetals, and these are atoms that love to gain electrons. Let's face it, what's happening in both of these cases that the 2 fluorine atoms are each gaining an electron. The ionic bond, you had someone who liked to lose an electron next to someone who liked to gain an electron. So for the ionic bond, you have a metal and a nonmetal, right? Well, you can have a metal and a metal get together, and we describe that as the metallic bond. Now what we're talking about is having a nonmetal and a nonmetal together. And we've got all the bases covered. Describing here the third type of chemical bond where atoms are being held together, and invariably it's an electrical force, right? But there are little twists in the story of how that electrical force is at play. For the ionic bond, there ain't no sharing. For the metallic bond, everybody's lost their electrons. And for the covalent bond, you have sharing, a sharing of the valent electrons. Any questions? So what we've just described are 2 atoms of the same kind coming together. And note that these are nonmetal atoms. But you can take different nonmetal atoms, different kind of nonmetal atoms, and put them together. Let's pick, how about oxygen, all right? Okay, oxygen. We're going to do oxygen. Describe the electron configuration for an oxygen atom. Go. Oh, I'm sorry. Oxygen has 8 protons with 8 surrounding electrons. Hey, excellent. Okay, so you got 2 electrons in the first shell, and you've got 6 electrons in the second shell. Now, how are those 6 electrons organized? I mean, in terms of like being paired and not paired. Ooh, got to think about that, huh? Yeah. Think of the double seats on the school bus. You have 6 electrons. The first 4 are going to pile into that bus and occupy their own seat. There's going to be no pairing upon the input of the first 4 electrons into that second shell. But we've got 2 more electrons to throw in there. And the 5th electron comes in and sees the 4 seats already filled. It's going to have to pair with somebody. Okay, so that's 1 pair. And then the 6th electron comes in and it's going to have to do the same thing, pair with somebody else. So for the oxygen, you've got 2 pairs of electrons and 2 unpaired. That is to say, 2 singlets, right? For the hydrogen atom, recall it had 1 unpaired electron in its valence shell. For the fluorine atom, it also had 1 unpaired valence electron. For the oxygen we find, it has 2 singlet electrons, unpaired valence electrons, right? That would mean it has 2 electrons to share. So, once upon a time, you had an oxygen atom minding its own business with in its outer shell, 2 pairs of electrons paired up, that's 4, and 2 singlets. I'm using the words interchangeably, singlet or unpaired, same. And there it was minding its own business when along came a hydrogen atom. The hydrogen atom with just 1 singlet electron. And that electron looked to the empty space next to one of the singlets in oxygen and saw, +6? If it could only be there, it could enjoy a +6 nuclear charge. +6 because the 2 inner shell shielding electrons hide the +8 in the nucleus. Got that? So it comes along and it binds by a covalent bond. You now have a covalent bond between the oxygen and a hydrogen. But we're not done. The oxygen has 2 singlets. And so along comes a second hydrogen atom, and its valence electron falls into that empty space next to that other singlet, and you form a second covalent bond. Here we've got a situation where there's an oxygen atom now covalently bonded to 2 hydrogens. And what do you call that? H2O. Water. Excellent. Also known as dihydrogen monoxide. Di meaning 2 hydrogens, dihydrogen monoxide, 1 oxygen, dihydrogen monoxide. Great. And to foreshadow something we're coming up to a bit later in this episode, notice that for that water molecule, look there at the oxygen atom. Yeah. And on the outside, you're going to see there are still 2 paired electrons, 2 sets of electrons that are paired. They're not bonded to anything. They're just paired out there in the valence shell of the oxygen atom, right? So you've got those 2 paired electrons, and they're not bonding, but you have those 2 singlets from the oxygen that are now bonding. They are bonding. And the total number of, let's say for a better word, things, the total number of things emanating from the oxygen atom, well, you've got a pair going this way, a pair going another way, and then you have a covalent bond to hydrogen in another direction, and a second covalent bond to a hydrogen in yet another direction. There are 4 things emanating off of that oxygen atom. 2 of them are paired electrons, and 2 of them are the covalent bonds. And notice there are 2 electrons within any covalent bond, and we can call them the paired bonding electrons. Great. We're going to come back to that. What? Oh, you want to do one more? Okay. Pick an atom, any atom. Carbon? Okay, carbon. All right. What is the electron configuration for a carbon atom? Excuse me. 6 protons, 6 electrons, which you get from the periodic table, of course. Go ahead. Carbon, yeah. Excellent. So you got 6 electrons, 2 of them are buried in the first shell, and you've got 4 electrons in the outer shell. Roger that. Okay, great. Describe the electron dot structure for carbon. Yeah, excellent. You've got 4 dots to worry about, 4 electrons in the second shell. And they're going to be singlets, right? Because remember, there are 4 double seats on that bus, and you got only 4 electrons. They're going to all occupy their separate seats. Great, yeah. And so you have a C in the middle, carbon, and then northeast, southwest, ... Right? Cool, all right. So you see there with a carbon atom, you have 4 singlets. Another way to say it is, there with a carbon atom, you have 4 empty spaces. Think of the double seats on the bus. You have 4 empty seats now, don't you? Now, you could have an electron come in and fill that seat. But what if that electron were attached to a hydrogen atom, right? So once upon a time, there was this carbon atom with its 4 singlet electrons. And along came this hydrogen atom with its 1 singlet electron. And it went right into one of those empty seats. And you now have a covalent, sharing valent electrons, covalent bond between that carbon and that 1 hydrogen. It did it once. How many more times could it do it? Yeah, 3 more times, for a total of 4 times. Recognize that carbon can form 4 bonds to 4 different hydrogen atoms. And so I think you're getting the trend here. Carbon tends to form 4 bonds. Oxygen tends to form 2 bonds. And fluorine tends to form 1 bond, covalent bond. What we haven't talked about is nitrogen. Go ahead in your spare time, figure out the electron configuration for nitrogen, and you will see that it has 3 singlets, which means nitrogen can form 3 covalent bonds. Cool? Yeah, look to the periodic table. Look at the sequence from boron to carbon to nitrogen to oxygen to fluorine to neon. Boron can form 3 covalent bonds. Carbon can form 4. Nitrogen 3, oxygen 2, fluorine 1, neon none. Yeah, it's a periodic trend. The number of covalent bonds that an atom can form, a nonmetal atom can form, is given by its atomic group. Interestingly, the elements above and below carbon in the periodic table all tend to form 4 covalent bonds. The elements above and below nitrogen tend to form 3 covalent bonds. The elements above and below oxygen, there's nothing above oxygen. Below oxygen is 2. Everything below fluorine, those all form 1 covalent bond. And everything below helium and neon, they don't form covalent bonds. There's no room in their outer shell. Awesome. Here, we need to talk about double covalent bonds and triple covalent bonds. What the heck is that? Let's go back to oxygen. You ready? I mean, are you really ready? Okay. Oxygen. The electron configuration for oxygen, we now know, is in the outermost shell, you have 2 pairs and 2 singlets, right? The oxygen is able to form 2 bonds. And we saw with water, it formed a bond with 2 different hydrogen atoms. We got H2O. But what about this story? Once upon a time, there was an oxygen atom with 2 singlet electrons. And along came another oxygen atom also with 2 singlet electrons. Yeah, and you formed a covalent bond between that oxygen and the other oxygen. Got it. But each oxygen still has another singlet. Remember, each oxygen can form 2 bonds. And so those 2 other electrons join together to form, get this, wait for it, a second covalent bond. Yeah, you can have 2 covalent bonds between just 2 atoms, oxygen atoms in particular here. And We tend to represent a covalent bond as just a straight line between the two atoms being covalently bonded. So to represent the double bond, we draw two lines between the oxygen and the oxygen. What do you suppose is more difficult to break apart, a single bond or a double bond? That's right. With a double bond, you got a lot more forces involved there. And so if you wanted to pull those two oxygen atoms apart, good luck. There's a lot of force to overcome. It's more difficult. So the double bonds tend to be stronger. And if you go through the same discussion with nitrogen, which has 3 singlets, it forms 3 bonds, you can actually have a nitrogen atom bond 3 times with another nitrogen atom. And we will call that a triple bond, which is exceedingly strong. That's why the nitrogen molecule, N2, is so incredibly stable. The nitrogen molecule is incredibly stable. It makes up almost about 80% of our atmosphere here on Earth. Wow. So covalent bonds, they're versatile. Covalent bonds, in my mind, are like Lego bricks. You know, you can just start putting the atoms together and you can start building atom by atom. And what exactly is it that you're building? Well, we saw with hydrogen and oxygen, we built a water molecule. With carbon, hydrogen, 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 you built a CH4 molecule, which is methane. With nitrogen, add 3 hydrogens, you have ammonia. We're building what are called molecules. I've been using this term now, molecule. I can formally introduce you to it. A molecule is another word for a covalent compound, right? A bunch of atoms held together by covalent bonds. Wow. Hey, how you doing? All right. Hey, that's pretty good. Yeah, we are now in the section where we're going to talk about the shape of molecules, right? So what we just went through describing the covalent bond, pretty powerful stuff. Just like Legos are pretty powerful. We just described how those Lego bricks stick together, right? From the Legos, you can build just about any structure. The same thing here. By virtue of the covalent bond, you can build just about any structure. Molecules, really. Big and small. Big molecules such as deoxyribonucleic acid. That's pretty important. But let's spend a little bit of time talking about the shapes of these little beasties that we call molecules. And a good place to start is with the methane molecule. Methane is CH4. You have a carbon in the middle, surrounded by 4 hydrogens. Now, here's what you can do. Try drawing that on paper. And you're going to be tempted to put the carbon right in the middle. And straight up, you'll have a hydrogen. To the east, you'll have another hydrogen. To the west, you'll have another hydrogen. Down south, you'll have another hydrogen. Measure the angles between those hydrogen atoms. Yeah, it's 90 degrees. You have it on a flat piece of paper, northeast, southwest. The thing is, though, molecules aren't two-dimensional. That piece of paper you just wrote it on, that's two-dimensional. Not good. Molecules, sorry about this, are 3-dimensional. And here's an important thing. That's all important, but pay attention. What's on the outside of any atom? Starts with L. That's right. The electron. There are electrons on the outside of any atom, right? So look at that methane molecule. Now, focus on the hydrogen atoms surrounding the carbon. And what's on the outside of any one of those hydrogen atoms? Starts with L. L electron. Yeah, they're electrons. Now, put yourself in the point of view of that electron. Pick one hydrogen atom. Okay, that one. All right, you are now the electron whizzing around that hydrogen atom. And interestingly enough, you're also being shared with a carbon because that's a covalent bond, but let's move forward. That electron on the outside of that hydrogen atom bears a negative charge. Now, look over to your adjacent neighboring hydrogen atom. What do you see? Oh, it too has an electron whizzing around on the outside. How do you feel about that? And how does it feel about you? Yum, yum, or yuck, yuck? Remember, negative charges repel negative charges, right? You are repelled, actually, by that other hydrogen. In fact, you're repelled by all the other 3 hydrogens that are there. What are we talking about? We're talking about a carbon in the middle with 4 hydrogen atoms extending from that carbon. Now, from the point of view of a hydrogen, it looks to the neighboring hydrogens and it would like to be as far away as possible. Now, I'm very proud of you. When you drew that methane molecule on the piece of paper, you put a carbon in the middle and you put a hydrogen up north, a hydrogen down south, a hydrogen to the east, a hydrogen to the west. You did not bunch them all together to one side of the carbon. The carbon, and then you went, all the hydrogens scrunched together to one side. No, you intuitively knew that those hydrogens would spread out to be as far apart as possible. And that's why you have a 90-degree angle between them on your piece of paper. Good job. But in a 3-dimensional world, you can do better than 90 degrees. For these hydrogen atoms wanting to get as far apart as possible, they want something greater than 90 degrees, and you get that when you're in 3 dimensions. Enter the tetrahedron. A tetra means 4, hedron means face. It's a geometric shape that has 4 faces. It kind of looks like a pyramid, but it's not a pyramid. A pyramid has a square at its base, if you want to get technical. If you want to make a tetrahedron, just get some bread dough and pinch it between your fingers, your thumb and index finger on both hands, and you're going to get yourself a tetrahedron. It's a 4-sided dice. Yeah? It's 3-dimensional, too. Consider what's going to happen with that methane molecule is that each of those hydrogens are going to occupy one of the vertices of that 4-sided dice. And they will stretch themselves out into 3 dimensions to get as far apart from each other as possible to form this tetrahedral shape. You'll find a picture of the tetrahedron. I know in the book you can find pictures of tetrahedrons online. And gosh, we'll even put a picture of a tetrahedron in the show notes at conceptualscience.com, right? It's a pyramid with triangles on all faces. So the shape of a methane molecule we find is not flat. The shape of that molecule is that of a tetrahedron. Why? Because the hydrogen atoms are trying to get as far apart from one another as possible. And in 3-dimensional space, the tetrahedron allows for that. The angle between the hydrogens in a tetrahedron is on the order of 109 degrees. And 109 degrees, that's bigger than 90 degrees. All right? That's methane. Any questions? Oh, okay. Another example. Pick a molecule, any molecule. You're good. Okay, water. Let's do water. All right, so what do we got with water? We've got an oxygen and we've got 2 hydrogens. The oxygen is covalently bonded to 2 hydrogens, right? What are the total number of things, for lack of a better word, coming off of that oxygen atom? Well, we got a pair going this way, a pair going that way, a bonded pair going one way, and a bonded pair going another. We have 4, the total of 4 things coming off of that oxygen atom, right? guess what shape they're gonna form? Whenever you have four things coming off of a central atom, oh, okay, let's not use the word thing. Let's get technical. Let's create a word. I don't know. How about substituent? I know, I say that to friends and they're like, what are you talking about, substituent? I mean, it's a chemistry term. In the world of chemistry, the word substituent means a thing coming off of a central point, right? So bear with me here. There are four substituents coming off of that oxygen atom. Name them. Okay, good. There's a hydrogen coming off one. Yeah, a hydrogen there. And there are two more. What are they? Oh, those paired electrons. Yeah, they're not bonded to anything. They're just paired. And you know those are electrons in the outermost shell of oxygen. Okay, really good. Okay, there are four. There are four substituents coming off of them. And do you suppose they want to be 90 degrees from each other? Like if you were to draw it flat on a piece of paper? No. It's three-dimensional. That's right. So those four substituents are going to spread themselves out into a tetrahedron. They're going to form a tetrahedral shape. Cool. Or let me say tetrahedral geometry. Because when we talk about the word shape, we actually mean something very specific. When you want to talk about the shape of a molecule, you don't pay any attention to the non-bonded pairs. You pay attention only to the atoms. Now, that should make sense. You want to know the shape of a water molecule? Well, you got to look at the relative orientation of the hydrogen, oxygen, and hydrogen, right? Okay, well, one hydrogen occupies one vertice of that tetrahedron, oxygen in the middle, and the other hydrogen occupies another vertice, right? And a lone pair occupies the third, and another lone pair occupies the fourth vertice. But let's now ignore the lone pairs and focus just on the hydrogen and oxygen atoms. Measure the angle between those, and you're going to come up with 109.5 degrees. Oh, the shape of a water molecule is bent, as opposed to linear, all falling on a straight line. No, there's this bend to the water molecule. You've seen it all the time. Whenever somebody draws a water molecule, it's not in the hydrogen, oxygen, hydrogen drawn in a line. No, they, for some reason, draw the hydrogen, oxygen, hydrogen at an angle, you know? And that angle should be, because it is, 109.5 degrees. Why? Because that's the angle you'll get between two vertices of a tetrahedron. That's why. Yeah. So the shape of a molecule is a study of the relative orientation of just the atoms. Now, although we ignore the lone pairs, you need to understand the lone pairs play a very important role. If it weren't for those lone pairs on the oxygen, the hydrogens would be 180 degrees apart from each other in a line. They would. But you have this repulsion between the entities at the vertices, the bonding pairs and the lone pairs, that they move as far apart from one another as possible. And what we have described here is a thing called valence shell electron pair repulsion, VSEPR for short. Valence shell, we're talking about electrons in the valence shell. Electron pair, now there are two types of electron pairs. There are the pairs that are just lone pairs. They're not bonded to anything. And then there are the pairs that are actually within a bond. Within that covalent bond, you've got two electrons and they're paired, right? So there are two types of paired electrons, the bonded and the non-bonded. Valence shell electron pair repulsion. Electrons repel each other. It just means they want to be as far apart from one another as possible within three-dimensional space. What? Okay, let's do another one. Pick a molecule, any molecule. Make it simple. Ammonia? Okay, ammonia. Ammonia is NH3, right? Go through the whole process, you'll find there are 3 hydrogens coming off that central nitrogen, and on top of that nitrogen, you've got a lone pair, right? So how many things, let's get technical, how many substituents do you have coming off of that nitrogen? 4. You got 4. You got 3 hydrogen atoms and a lone pair, right? And they're going to spread themselves out as far apart as possible, electron pair repulsion. And that geometry is going to be tetrahedron. Yeah, it's going to be a tetrahedron. Now, what do you find at the vertices of that tetrahedron for an ammonia molecule? Let's say at the top vertex, you got a lone pair. How do the bottom 3 vertices, corners? Yeah, you got hydrogen atoms. So the geometry of ammonia is tetrahedral. But what about the shape? Just focus on the atoms. Put a blind eye to that lone pair that's up on top. And you'll have a nitrogen atom, and you'll see hovering above 3 hydrogen atoms. And it's kind of like a pyramidal shape, isn't it? What do they call that? I think they call that trigonal pyramidal. And call it what you want. Understand what it is. And you're ahead of the game. Big time. Okay, let's start this next section with a bit of review. Let's look at the hydrogen atom. Remember what happened there when 2 hydrogen atoms got together? They each have an electron that they share with the other. And when they both do that, you'll have 2 electrons in between the 2. And those electrons are being shared by those atoms, much like 2 toys being shared by kids. It's the attraction those kids have for the toys that holds them together. The toys are like glue. Likewise, for the hydrogen, it's the attraction those nuclei of the hydrogen have for those shared electrons that holds those 2 hydrogen atoms together. Their mutual attraction for the electrons that they share is a force, and we call that the covalent bond. But when we talk about sharing now, understand that hydrogen atoms are hydrogen atoms, and they all have the same properties because they're the same atom. What might happen if you had a covalent bond between 2 different types of atoms? All right, let's pick hydrogen on one side and, fluorine? Okay, fluorine on the other. And let's look at a covalent bond forming between hydrogen and fluorine. Okay, electron. Let's say you're the electron in the hydrogen atom, right? And you look down to the nucleus and you see a +1, and that's pretty good, that holds you there. But then you look over to the fluorine, and that empty space in the second shell of the fluorine atom has an effective nuclear charge of +7. That is to say, from that point of view there in the second shell, you look down to the nucleus, and it looks like a +7. I know it's +9, but there are 2 electrons in your way, right? So there you are, the electron, and you and the hydrogen atom jump over to the fluorine, and you fill the empty space within that second shell of the fluorine atom. And you have, sure, a covalent bond between a hydrogen and a fluorine, 2 different atoms. It works. Yeah, okay. But now let's talk about what those 2 bonding electrons witness. Bonding electrons. Those are the 2 electrons, the pair of electrons that are holding the hydrogen and the fluorine atoms together. Those 2 electrons, they look toward the hydrogen nucleus and they see a +1. But when those 2 electrons turn around and look at the fluorine nucleus, they see a +7, an effective nuclear charge of about +7. So, wait a second. One way, there's a +1 pulling on you, and the other way, there's a +7 pulling on you. You see, You'd have a preference for the +7, very much so. And what we have here is a situation where, with two different types of atoms, the sharing is not even. You have uneven sharing. The fluorine has a greater attraction for those electrons, or from the electron's point of view, they look down at the fluorine nucleus and they see a greater nuclear charge. They are pulled in preferentially toward the fluorine. So if we want to represent that, the idea that those electrons are not being shared evenly, that those electrons tend to spend most of their time close to the fluorine, there's a way to do that. When you draw the bond, you can just put two dots as the covalent bond between the two atoms. Now, should those two dots be evenly spaced between those two atoms? Or might you draw them such that they're a bit closer to the fluorine? Yeah. And when you do that, draw it so those electrons appear to be a bit closer to the fluorine, you're acknowledging the fact that the fluorine has a greater nuclear charge. It's pulling them in toward it. This is a concept called electronegativity. Big word. Electronegativity. It means the pulling power. The pulling power of an atom. Pulling power. What do you mean pulling power? The ability to pull on electrons that are being shared. Those two electrons between the hydrogen and the fluorine is able to pull harder on those two bonding electrons than is the hydrogen. The fluorine has a greater electronegativity, a greater pulling power, and it pulls those two bonding electrons toward it. Now, what's happening here is the electron from the hydrogen is now spending most of its time around the fluorine. It's not being shared evenly. And because it's spending more of its time around the fluorine, that fluorine now effectively has a bit more negative charge than it normally does. It's an extra electron that came from the hydrogen. And we're going toward the argument of a ionic bond now, aren't we? But not quite, because there is still significant sharing that occurs. But what we find is that the fluorine atom tends to pick up this slightly negative character. In the hydrogen, because it's frankly losing electron to fluorine, becomes slightly positive in character. And so we can represent that by using the delta, lowercase Greek delta symbol. And we say the fluorine is delta negative, which means slightly negative, and the hydrogen is delta positive, which means it's slightly positive. There's uneven sharing. And in this situation, the fluorine side is slightly negative, and the hydrogen side is slightly positive. This is what physics types call a dipole. And if you were to look at that bond between the hydrogen and fluorine, you would say, oh, look, it has a dipole, because one side's slightly negative and one side's slightly positive. Yeah? And what we're talking about here is bond polarity. If you have perfect sharing between the two atoms, there's no polarity at all. But when you have two different atoms with two different electronegativities, pulling powers, then you end up with what we call a polar covalent bond. Now, relative to the periodic table, the atoms of elements to the upper right side of the periodic table, such as fluorine, chlorine, and oxygen, those are the atoms with the greatest electronegativity, the greatest ability to pull electrons toward themselves. Remember, the nonmetals, they tend to gain electrons. That's pulling electrons towards themselves. The farther to the upper right in the periodic table, the greater the electronegativity. Conversely, to the lower left of the periodic table, you have atoms of elements that have low electronegativity. And what are you going to get when you take an atom with a low electronegativity, such as sodium, and put it together with an atom with a high electronegativity, such as fluorine or chlorine? That's right, the ionic bond, that's what you get. But what do you get if you take two nonmetal atoms and you put them together? You're going to get a covalent bond. But if you have something like carbon and fluorine together, they have different electronegativities. You're going to find the fluorine with its greater electronegativity is going to pull on the electrons, the bonding electrons, away from the carbon. The fluorine, because of its greater pulling power, it gains a slight negative charge, while the carbon gains a corresponding slight positive charge, and you have a polar covalent bond. Perhaps the best example to talk about is with the water. Recall that the shape of a water molecule is bent. So let's look at each of the hydrogen-oxygen bonds one at a time. Think of water, HOH. Now, let's look at the bond between a hydrogen and the oxygen. And ask yourself, which has a greater electronegativity, the hydrogen or the oxygen? You could use our dear old friend, the periodic table, to see that oxygen is closer to the upper right than hydrogen. And so the oxygen has a greater electronegativity. It's going to pull on the bonding electrons away from the hydrogen and thus become slightly negative. So that hydrogen-oxygen bond is a polar covalent bond. Do one hydrogen-oxygen bond, you can do the other. And that, too, is going to be a situation where the oxygen is slightly negative and the hydrogen is slightly positive. And so what's happening here is the oxygen is literally pulling on those shared electrons from the hydrogens to become slightly negative in itself. So the oxygen side of any water molecule is going to be slightly negative. It comes down to the greater effective nuclear charge of that oxygen atom. And the hydrogen side of your water molecule is going to be slightly positive. So you can have a bond that's polar, but what we're looking at here is actually an entire molecule that's polar. Looking at the shape of that molecule, you'll find the oxygen side is slightly negative and the hydrogen side is slightly positive. So what might happen with another water molecule? Well, it's going to be the same thing. It's going to have the same shape. It's going to have the same atoms, H2O. And the hydrogen-oxygen bond is going to be slightly negative on the oxygen side, positive on the hydrogen side. Multiply that by 2 because you have 2 oxygen-hydrogen bonds, and you've got the oxygen side is slightly negative and the hydrogen side of your molecule is slightly positive. Great. Yeah, same, because it's the same molecule. It's a water molecule. And that's the case for all water molecules. Now, take 2 water molecules and put them together. They're molecules. That means they're unique entities in and of themselves. And we've been talking about the intramolecular forces, what's going on within the molecule, the covalent bonding within the molecule, and this added nuance that covalent bond can be polar because of uneven sharing. That's all going on within a water molecule. And as a consequence, you have the oxygen side slightly negative and the hydrogen side slightly positive. But what about intermolecular forces? Not intramolecular, but intermolecular, which means between separate molecules. How might 2 separate water molecules feel about each other? Well, you know what? The oxygen side's slightly negative on one water molecule, and the hydrogen side is slightly positive on another water molecule. Don't opposites attract? Yeah. So the oxygen side of one molecule is going to attach itself to the positive side of another water molecule. There is going to be an attraction between the two. How strong? Not that strong. The covalent bond, if the covalent bond is a strength of 100, this interaction between these 2 water molecules, it's going to be about 5. But it's real. It's very real. And it's what makes water sticky. Water loves to stick to water. Water molecules are sticky, and now we know why. Because of the polar covalent bonds within each molecule. And because the water molecules are so attracted to each other, that means transforming it from a liquid to a gaseous phase, that takes a lot of energy. And that means here at room temperature, water, H2O, is found in the liquid phase. Remember, in the liquid phase, the molecules are all tumbling over one another. In the gaseous phase, you have fully separated them from each other. It's difficult to fully separate these water molecules from each other. Why? Because they're attracted to each other. They're sticky. What? Oh, okay, let's do one other molecule. And then actually, we've got this whole discussion of covalent bonding finally wrapped up. Let's do carbon dioxide. All right, so that's CO2. And if you go through the VSEPR, you'll find CO2 is a linear molecule. You have oxygen, carbon, oxygen, all in a line. And in fact, there are double bonds between the carbon and the oxygens. All right, let's look at one of those covalent double bonds between carbon and oxygen. And in the periodic table, we see that oxygen has a greater electronegativity than the carbon. So the oxygen's going to pull those bonding electrons away from the carbon toward itself. It has greater pulling power, a greater electronegativity. And so that oxygen's going to be slightly negative and the carbon's going to be slightly positive. That's one bond. Let's do the other. The other is on the opposite side of the molecule, in the opposite direction. So you'll have that oxygen on the opposite side pulling electrons toward it. And the carbon goes, okay, I'm going to give you my electrons, but there's an oxygen on the other side of me that's pulling them back the opposite way. One oxygen is pulling electrons toward the right, but the other oxygen is pulling them back to the left. It's a wash. It's a tug of war where two people are pulling on a rope with an equal force in opposite directions. The rope goes nowhere. Likewise here with the carbon dioxide, the electrons go nowhere. One oxygen tries to pull them this way, the other oxygen just pulls them right back. There's a balance. And that has everything to do with that the carbon dioxide molecule is linear, unlike the water molecule, which is bent. Having the linear shape makes it so that those pulls are equal and opposite, and thus cancel each other out. That's how it is that the carbon dioxide molecule is nonpolar. And so, how might two carbon dioxide molecules feel about each other? There's no stickiness involved. And the two molecules might just bounce off one another and not stick. And that's what we know to be the case within a gaseous phase, which is exactly why carbon dioxide is a gas at room temperature. Exhale your breath. Carbon dioxide coming out of your mouth is a gas. Hold a glass up to your breath and do the same thing. And you'll see that the water condenses on the glass. At the same temperature, the water is a liquid. Water's a liquid because the molecules are sticky. Carbon dioxide is a gas because the molecules are not sticky. They're nonpolar. So let me ask you, which is heavier? A carbon dioxide molecule or a water molecule? Well, let's add it up. Water, you have oxygen, that's 16, a mass of 16 from the periodic table. Hydrogen, that's 1. You have 2 of them, so 2. The total mass of a water molecule is 18 atomic mass units. Okay. What's carbon dioxide? Carbon is 12, a mass of 12 from the periodic table. Oxygen is 16 from the periodic table. 16 plus 16 is 32, plus 12 is 44. The mass of a carbon dioxide molecule is 44. What was the mass of water? It was 18. Carbon dioxide is over twice as massive as water. Carbon dioxide is over twice as massive as water, and yet it's a gas at room temperature, and water is a liquid. How can that be? Oh, well, a quick summary. You see, the hydrogen-oxygen bond in the water molecule is polar because the oxygen pulls on the electrons away from the weaker hydrogen. Oxygen has a stronger electronegativity. And the shape of the water molecule is bent. It's not linear, it's bent. So that means the two dipoles within those two bonds don't cancel each other out. In fact, they add up to some real number, which makes the oxygen side of the water molecule negatively charged, and the hydrogen side slightly positively charged in character, which makes it so that two water molecules stick. Don't worry about the mass. It's the stickiness that matters. But why is water bent? Why does water have that bent shape? Of course, it's because of the two lone pairs on the oxygen. You know, if it weren't for those two lone pairs on the oxygen, water wouldn't be bent. Water would be linear like carbon dioxide, and the dipoles would cancel out, and the water would be nonpolar, and the water would be a gas at room temperature, and we wouldn't have our oceans. In fact, we probably wouldn't have us either, which is why we can be most thankful for those lone pair electrons on the oxygen of a water molecule, which makes the water molecule bent, which makes the water molecule sticky, which makes water a liquid at room temperature. That's good chemistry. Good chemistry to you. Theme music by Zach Jeffrey, musical flourishes by CPro Music, production assistance from Greg Simmons, and thanks to you, the listener, our co-host for this special episode on covalent bonding. A note of appreciation to all instructors using Conceptual Academy. Thank you for your support. And to the hardworking student, our thanks to you as well for your learning efforts, which we see as the path to making this world a better place. There's a bigger picture. That's good chemistry. Good chemistry to you.